Welcome! Today we're diving into Apache Kafka, technology used by Netflix, Google, LinkedIn, and basically every major tech company. By the end of this video, you'll understand what Kafka is and why it is so powerful, and how it solves real problems in production systems. But before we go, please hit that like button, subscribe, hit notification bell. It's really helped me to grow this channel. Thank you. Let's start with the basics. A typical web application has the three main components: a front-end, your browser or mobile app, the back-end, the server that runs the actual application logic, and the database where the data gets stored. The front-end talks to the back-end through HTTP requests. The back-end processes those requests and communicates with the database to store or retrieve the data. Pretty straightforward. Traditionally, developers built entire backends as monoliths. One giant codebase with all features running on a single server as one application. This works fine when your app is small, but as your application grows, problems emerge. Your codebase becomes massive and harder to maintain. A single code change now affects the entire system. Deploying the features becomes riskier because everything is tight connected. Scaling becomes expensive because you need to scale the entire monolith, not just the part that needed. This is why the industry moved to microservices. Instead of one giant application, you break it into small, independent microservices. Each service has its own codebase, run on its own server, and handles one specific responsibility. The post services handles post. The notification service sends notification. The user service manages users. Now development becomes faster, deployment is safer because changes are isolated. Scaling is cheaper because you only scale the service that needed. Here's where things get tricky. With the microservices, these independent programs need to communicate with each other. They can't just call functions in the same codebase anymore, they own the different computers. The traditional approach is to have the services communicated directly via HTTP. Service A sends a request to service B, waits for a response, and continues. Seems simple enough, right? But this approach has serious problems. Networks are unreliable. When you send data over the internet, there's always a chance something goes wrong. The connection might drop, the data might get corrupted, the response might never come back. You have no control over this. It's just the nature of networks. Synchronous blocking. When service A sends a request to service B, it has to wait around doing nothing until it gets a response. If a service B is busy processing other requests, service A just sits there waiting. If service B is doing something that takes a long time, service A is blocked the entire time. Your whole system becomes as slow as the slowest operation. Data loss on failure. Let's say service A sends the payment request to service B. Service B receives it and starts processing the payment. But halfway through, service B server crashes. The power goes out, a hard drive fails, the processing stops, and that data was only stored in RAM. When the server comes back up, that payment information is just gone. This is catastrophic for critical operations. You can't lose payment data, you can't lose user registration, you can't lose order information, but with this direct HTTP approach, you can. Tight coupling and scalability. Imagine your post service needs to send notification to users. At first, you hardcode the notification service's address into the post service. It sends HTTP request directly to the notification service. Then later, you add an analytical service that also needs the post data. So you modify post service to send requests to both the notification service and the analytical service. Then you add a recommendation service, and you modify the post service again. Every time a new service needs your data, you have to change the producer service's code. This creates bugs, it's time-consuming, it is not scalable. All these problems led developers to invent message brokers. A message broker is a separate program that sits in the middle of your architecture. It acts as intermediate between services. Instead of services talking directly to each other, they all talk to the message broker. Here's how it works. A producer sends data to the message broker. The message broker stores this data reliably. Then, when a consumer is ready, it pulls data from the message broker and processes it. This simple concept solves all problems we mentioned. Now the producer doesn't wait around. It sends the data to the broker, gets confirmation that the broker received it, and immediately continues with the other work. The producer doesn't care when the consumer processes the data. It might be immediately, it might be in an hour later, the producer just knows that broker has it and will deliver it. The message broker stores data on disk, not just in memory. If a consumer crashes in the middle of the processing, this data isn't lost. The message broker still has it. When consumer comes back online, it retrieves the message and continues processing. The producer doesn't know how many consumers exist, it doesn't care, it just puts the data in the broker. Any services that interesting can connect to the broker and consume that data. You can add the new consumer without touching the producer's scope. Message brokers typically run on the multiple servers. Data gets replicated across those servers. If one server fails, another has the data, nothing is lost. You can easily add more consumers to handle more load. The system scales horizontally without changing the producer. Several message brokers exist. ActiveMQ, RabbitMQ, Redis, they can all work, but Kafka has become the industry standard. Why? Because Kafka has a special architecture designed to handle massive scale. We are talking millions of messages per second. Netflix use it, Uber use it, LinkedIn create it. Here's something important. Kafka isn't just a simple pipe, where you throw all your data in one end. Kafka organizes messages into topics. Think of topics as channels. Each topic is dedicated to a specific type of messages. You might have a post topic for all messages about posts, a comments topic for comments related messages, a likes topic for likes, a payments topic for payments events. When a producer publishes a message, it specifies which topic it belongs to. A consumer subscribes to a specific topic. If a consumer subscribes to the payments topic, it only receives the payments related messages. It knows every message it gets is about payments. No need to filter or analyze. This organization gives you two huge benefits. First, consumers don't get confused by a giant stream of mixed data. Second, different services can produce and consume from different topics independently. Your post service publish to the post topics, your notification service consume from the post topics, your analytics service also consume from the post topics. They don't interfere with each other. Now, here is a critical question. What if something goes wrong during the message delivery? Kafka gives you options. At most once delivery. With this setting, Kafka doesn't guarantee you anything. The message might be delivered exactly once, or it might be lost completely, 0 times. Why would you use this? Speed. If you're not worrying about losing messages, you can optimize for pure speed. No retry logic, no fancy storage, messages zip through. This works for non-critical data like analytics or logs where losing a few events doesn't matter, at least once delivery. This is the guarantee most people use. Kafka guarantees every message arrives at least once, possibly more than once, but at least once. Here's how it works. When a producer sends a message, it waits for a Kafka to send back an acknowledgement, a confirmation that says, I received this message and I save it to the disk. Only after getting this confirmation does the producer move on. If the confirmation is lost due to network error, the producer automatically retries. It sends the message again. Kafka receives it, save it again, and send back another confirmation. This retry mechanism ensures the message never gets lost. But here's the catch. The same message might exist in Kafka twice now, and both copies could be consumed. This is where idempotence comes in, a word you see everywhere in backend development. An idempotent consumer is the one that produces the same result whether it processes a message once or 10 times. For example, if you're processing a user profile update messages and it arrives twice, you consumer should just update the profile twice. The result is the same, the profile has the latest data. The duplication doesn't cause the problems. Exactly once delivery. The ultimate guarantee. Every message is delivered exactly once, no loss, no duplicates, perfect reliability. The trade-off, it's complex to implement and slower than the other options, but the critical operations like money transfer or medical records, it's worth it. Here is a rule, never run Kafka on a single machine in production, that's asking for a data loss. Instead, you run Kafka cluster, multiple Kafka servers running on the different machines, connecting together. When a message arrives, Kafka doesn't just save it on one server, it replicates across multiple servers. Server 1 has the message, server 2 also has it, and number 3. Now, if server 1 explodes tomorrow, server 2 and 3 still have all data, processing continues without interruption. No data is lost. This replication happens automatically. You configure it once and Kafka handles it. This is where Kafka magic happens. This is why Kafka can handle millions of messages per second. Each topic divided into partitions. A partition is like a separate queue within the topic. If you have a post topic with 5 partitions, you effectively have 5 parallel queues, all containing post messages. Instead of processing messages one at a time from a single queue, you can process from 5 queues simultaneously. More partitions equal higher throughput. It's that simple. When a producer sends a message to a topic, Kafka sends it to one partition, usually chosen to balance the load. A message about post number 123 might go to partition 2. A message about post 456 might go to partition 4. They are distributed across all partitions roughly evenly. On the consumer side, multiple consumers can read from different partitions in parallel. Consumers 1 reads from partition 1, consumers 2 reads from partition 2, and so on. This parallelization is what lets Kafka process massive volumes. Important note, messages are strictly ordered within the partition, but across partitions order isn't guaranteed. If you need to guarantee a specific order, you use a message keys. A message key is additional field you attach to your message. All messages within the same key go to the same partition. So if you always use the user ID as a key, all messages for that user go to the same partition and stay in order. Here's another benefit of partitions. They distributed data across your cluster. Imagine you have 5 partitions and 3 servers. You might put partition 1 and 2 on the server 1, partition 3 and 4 on server 2, and partition 5 on server 3. Now the processing load is spread across all 3 servers. Each server only handles a part of a total volume. As your volume grows, you add more servers and add more partitions, load distributes evenly, your system scales linearly. Kafka provides one more clever mechanism: consumer groups. A consumer group is just a name for a team of consumers that work together. Imagine you have the notification servers running on 5 different servers. For redundancy, all 5 copies belong to the same consumer group. Kafka distributes messages among the members of a group. If you have 5 partitions and 5 consumers in a group, Kafka assigns each consumer to one partition. Consumer 1 gets partition 1, consumer 2 gets partition 2, etc. Now you're processing from all 5 partitions in parallel. Your throughput multiplies. Here's what's clever. Different consumer groups can read the same topic independently. Your notification service group consumes from the post topics, your analytics service group also consumes from the same post topics. They both get all the posts, but they process them independently, without interfering with each other. If you have more consumers than partitions, some consumers sit idle. Each partition can only be handled by one consumer per group. If you have fewer consumers than partitions, some consumers handle multiple partitions. Different groups can consume the same topic with a zero interference. Offsets. Resuming from where you left off. Every message in partition gets a sequential number called an offset. First message is offset 0, second is offset 1, and so on. When a consumer processes a message from a partition, Kafka records this a consumer group has processed up to offset 47. This is called committing an offset. Why does this matter? If the consumer crashed, when it restarts, it doesn't start from offset 0 again. It starts from offset 48. It doesn't reprocess the messages it already handled. It doesn't skip unprocessed messages, it picks up exactly where it left off. There are 2 ways to commit offsets. Automatic commit: every few seconds the consumer automatically sends its current offset to Kafka. Easy but risky. If the consumer crashes between commits, it will reprocess some messages. Manual commit: after successfully processing a message completely, the consumer explicitly tells Kafka, "I am committing this offset." More reliable, you only commit after you're 100% sure message was processed, but requires more code. Because all messages have the same key, they go to the same partition and are processed in exactly the order you send them. Real-world use cases. Netflix processes billions of viewing events daily. When you watch a show, events flow through Kafka to update recommendations, track your viewing history, and measure engagement. Uber. Driver location updates, rider requests, passenger pickups, trip completions all happens as an event in Kafka. Pricing algorithms, ride matching, and notification depends on this real-time event stream. LinkedIn. Every action generates an event. Profile views, message send, job application, these flow through Kafka to update feeds, send notification, and power analytics. Reliability. Disk persistence and multi-server replication guarantee zero data loss. Scalability. Partition distributed across servers let you handle any volume. Netflix process millions of messages per second. Performance. Sequential disk writes and batch processing make Kafka incredibly fast. Flexibility. Topics completely decoupled producers from consumers. Add the consumers without changing producers. Guarantees. You choose your reliability level, at most once for speed, at least once for balance, exactly once for critical operation. Key components. Topics. Channel for different messages types. Partition. Parallel queues that enable massive throughput. Replication. Multi-server backup eliminate data loss. Consumer groups. Team of parallel processors. Offset. Position tracking for resuming interrupted processing. Delivery guarantees. Choose between speed, reliability, and perfection. Understanding this concept lets you design systems that handle real-world scale and reliability requirements. In the next video, we'll install Kafka, create topics, configure partitions, and build a complete working example with multiple producers and consumers running in Python. Thank you all for watching, see you in the next one!